When performing point-to-point short-circuit calculations and utilizing Table C to determine the F-factor, adjustments are necessary when employing multiple conductors for each phase. Specifically, when you have a run with 2 conductors for each phase, the F-factor obtained from Table C needs to be modified to accurately reflect the increased ampacity and reduced impedance of the parallel conductor configuration. The fundamental principle behind this adjustment lies in the fact that the total current flow through the phase is now distributed equally between the 2 conductors. This effectively increases the overall conductor size and reduces the impedance of the run. Consequently, the F-factor, which is inversely proportional to the conductor impedance, needs to be adjusted accordingly. The appropriate adjustment factor is the square root of 2, approximately 1.414. This factor arises from the relationship between the impedance of a single conductor and the combined impedance of 2 identical conductors in parallel. When 2 identical impedances are placed in parallel, the equivalent impedance is halved. However, the F-factor is inversely proportional to the impedance, meaning that having the impedance results in an increase in the F-factor by a factor of 2. Since we are dealing with the square root of this effect, we multiply by the square root of 2. Mathematically, this can be expressed as follows. Let F represent the F-factor obtained from Table C for a single conductor. Let F adjusted represent the adjusted F-factor for 2 conductors in parallel. Then F adjusted equals F multiplied by the square root of 2. In this specific scenario where you have 2 4/0 American wire gauge conductors per phase, and the value obtained from Table C is 15,082, the adjusted F-factor would be calculated as follows. F adjusted equals 15,082 multiplied by the square root of 2. This results in an F adjusted value of approximately 21,317. Therefore, in your short-circuit calculations, you should use the adjusted F-factor of 21,317 to accurately represent the characteristics of the 2 4/0 conductors in parallel. To summarize the procedure, firstly, identify the appropriate F-factor from Table C based on the conductor size for a single conductor. Secondly, multiply this value by the square root of 2, which is approximately 1.414, to obtain the adjusted F-factor for 2 conductors in parallel. Thirdly, use the adjusted F-factor in your point-to-point short-circuit calculations to ensure accurate results. It is crucial to understand the underlying principle behind this adjustment. When multiple conductors are used in parallel, the overall impedance of the circuit is reduced. This reduction in impedance leads to a higher fault current. The F-factor is a critical component in the point-to-point calculation method as it directly influences the calculated fault current. By adjusting the F-factor appropriately, you ensure that the calculated fault current accurately reflects the actual fault current that would occur in a parallel conductor configuration. Failing to adjust the F-factor when using multiple conductors in parallel would result in an underestimation of the fault current. This could have serious consequences, such as inadequate protection, device coordination, and potential equipment damage. Therefore, it is essential to always remember to adjust the F-factor when employing multiple conductors per phase in short-circuit calculations. In addition to the square root of 2 factor for 2 conductors, it's important to understand how this adjustment generalizes to scenarios with more than 2 conductors per phase. The general principle is that the F-factor should be multiplied by the square root of the number of conductors per phase. For instance, if you have 3 conductors per phase, you would multiply the F-factor from Table C by the square root of 3, which is approximately 1.732. Similarly, for 4 conductors per phase, you would multiply by the square root of 4, which is simply 2. This generalization stems from the fact that the equivalent impedance of n identical conductors in parallel is the impedance of a single conductor divided by n. Since the F-factor is inversely proportional to the impedance, it should be multiplied by n. However, the F-factor appears in the denominator of the fault current equation under a square root, thus requiring the square root of n as the multiplier. To illustrate with another example, consider a scenario where you have four 250 kilo circular mills conductors per phase, and the F factor from table C for a single 250 kilo circular mills conductor is 9,500. To find the adjusted F factor for the four conductors in parallel, you would multiply 9,500 by the square root of 4, which is 2. This yields an adjusted F factor of 19,000. This value should then be used in your short circuit calculations. It is also important to consider the specific application and relevant codes and standards when performing short circuit calculations. The National Electrical Code, or NEC, provides guidelines and requirements for electrical installations, including short circuit protection. It is crucial to comply with all applicable NEC requirements to ensure the safety and reliability of the electrical system. Furthermore, it is recommended to consult with a qualified electrical engineer or other expert when performing short circuit calculations, especially in complex or critical applications. Short circuit calculations can be intricate and require a thorough understanding of electrical theory and applicable codes and standards. Seeking expert advice can help ensure that the calculations are performed correctly and that the electrical system is adequately protected. In summary, adjusting the F factor when using multiple conductors per phase in point-to-point short circuit calculations is a critical step in ensuring accurate results and adequate protection of the electrical system. The F factor should be multiplied by the square root of the number of conductors per phase. Remember to always consult with applicable codes and standards and seek expert advice when necessary. Understanding the fundamental principles behind short circuit calculations and the role of the F factor is essential for electrical engineers and technicians involved in the design, installation, and maintenance of electrical systems. By applying the correct adjustment factors and adhering to relevant codes and standards, you can ensure the safety and reliability of the electrical system and prevent potential damage from short circuit faults. For additional clarity, let's delve deeper into the mathematical reasoning behind using the square root of the number of conductors as the adjustment factor for the F factor. Consider a single conductor with an impedance of Z. The F factor is inversely proportional to this impedance. When n identical conductors are connected in parallel, the equivalent impedance, Z equivalent, is given by Z divided by n. The adjusted F factor, F adjusted, is inversely proportional to Z equivalent. Therefore, F adjusted is proportional to 1 divided by Z equivalent, which is equal to n divided by Z. Since the original F factor, F, is proportional to 1 divided by Z, we can write F adjusted as equal to F multiplied by n. However, the F factor is typically used within a square root in the fault current calculation formula. This means that the fault current is proportional to the square root of the F factor. Therefore, to account for the effect of multiple conductors, we need to take the square root of n when adjusting the F factor. This gives us the final formula for the adjusted F factor. F adjusted equals F multiplied by the square root of n. This formula accurately reflects the impact of multiple conductors on the fault current. Another important consideration when using multiple conductors per phase is the ampacity dirting factors that may be required by the NEC. The NEC specifies dirting factors for conductors in raceways or cables, especially when multiple current-carrying conductors are present. These dirting factors reduce the allowable ampacity of the conductors to prevent overheating and ensure safe operation. When performing short-circuit calculations, it is essential to use the derated ampacity values for the conductors. This will ensure that the calculated fault current is accurate and that the protection devices are properly sized to protect the conductors. The ampacity derating factors are typically expressed as percentages and are based on the number of current-carrying conductors in the raceway or cable. The NEC provides tables and guidelines for determining the appropriate dirting factors for various situations. It is important to consult the latest edition of the NEC and any applicable local codes and regulations to ensure compliance with all requirements. In addition to ampacity dirting factors, it is also important to consider the temperature rating of the conductors. The temperature rating of a conductor specifies the maximum temperature that the conductor can withstand under continuous operation. The NEC provides ampacity tables for different conductor temperature ratings. When selecting conductors for an electrical installation, it is essential to choose conductors with a temperature rating that is appropriate for the operating environment. The temperature rating of the conductors can also affect the short circuit withstand rating of the conductors. The short circuit withstand rating specifies the maximum fault current that the conductor can safely withstand for a specified duration. It is important to ensure that the conductors have a short circuit withstand rating that is adequate for the calculated fault current. In summary, when using multiple conductors per phase, it is crucial to consider the ampacity rating factors and the temperature rating of the conductors. These factors can significantly affect the calculated fault current and the sizing of protection devices. Always consult the latest edition of the NEC and any applicable local codes and regulations to ensure compliance with all requirements. Furthermore, it's worth noting that the point-to-point method, while generally accurate, relies on certain assumptions and simplifications. It assumes that the source impedance is constant and that the conductor impedance is uniform throughout the run. In some cases, these assumptions may not be entirely valid. For example, the source impedance may vary depending on the operating conditions of the power system. Similarly, the conductor impedance may vary due to factors such as temperature and conductor bundling. In situations where the assumptions of the point-to-point method are not met, it may be necessary to use more sophisticated short-circuit calculation methods such as computer-based power system analysis software. These software programs can model the electrical system in greater detail and account for various factors that can affect the fault current. Power system analysis software can provide more accurate and reliable results, especially for complex or critical electrical systems. While such software offers greater precision, it also requires more detailed system information and specialized expertise to use effectively. The point-to-point method remains a valuable tool for many applications, particularly for smaller or less complex systems where the added complexity of software-based analysis may not be warranted. The key is to understand the limitations of the point-to-point method and to use it appropriately. Always verify the accuracy of the results and consider using more sophisticated methods when necessary. Another important aspect to consider is the coordination of overcurrent protective devices, or OCPs. OCPs, such as circuit breakers and fuses, are designed to protect electrical equipment from overloads and short circuits. Proper coordination of OCPs is essential to ensure that the OCP closest to the fault clears the fault quickly and efficiently, while minimizing the impact on the rest of the electrical system. Short circuit calculations are a critical input to OCP coordination studies. The calculated fault currents are used to determine the appropriate settings for the OCPs. The settings must be chosen to ensure that the OCPs will trip quickly enough to protect the equipment from damage, but not so quickly that they will trip unnecessarily due to transient overcurrents. OCP coordination studies can be complex and require a thorough understanding of OCP characteristics and coordination principles. It is recommended to consult with a qualified electrical engineer or other expert when performing OCP coordination studies. The engineer can help ensure that the OCPs are properly coordinated and that the electrical system is adequately protected. In addition to short-circuit calculations, OCP coordination studies also involve analyzing the time current curves, or TCCs, of the OCPs. The TCC show the relationship between the current flowing through the OCP and the time it takes for the OCP to trip. By comparing the TCC of different OCPs, it is possible to determine whether they are properly coordinated. The goal is to ensure that the OCP closest to the fault trips before any upstream OCPs trip. This will minimize the impact of the fault on the rest of the electrical system. Furthermore, it's important to consider the impact of arc flash hazards when performing short-circuit calculations and OCP coordination studies. Arc flash is a dangerous phenomenon that can occur when a short-circuit fault creates an electrical arc. The arc can generate intense heat and light, as well as a pressure wave that can cause serious injuries or even death. Short-circuit calculations are used to determine the arc flash incident energy levels at various locations in the electrical system. This information is used to select appropriate personal protective equipment, or PPE, for workers who may be exposed to arc flash hazards. The NEC and other standards provide guidelines for performing arc flash hazard assessments and selecting appropriate PPE. It is essential to comply with all applicable arc flash safety requirements to protect workers from the dangers of arc flash. Arc flash studies also inform the design and implementation of arc flash mitigation strategies. These strategies may include the use of current-limiting devices, such as current-limiting fuses or circuit breakers, to reduce the magnitude of the fault current and the arc flash incident energy. Other mitigation strategies may include the use of remote racking devices to allow workers to operate electrical equipment from a safe distance. Arc flash safety is a critical aspect of electrical safety and should be a primary consideration in all electrical work. Finally, it's crucial to document all short circuit calculations, arc coordination studies, and arc flash hazard assessments. This documentation should include all assumptions, input data, and results. The documentation should be kept up to date and readily available for future reference. Proper documentation is essential for maintaining the safety and reliability of the electrical system. It also facilitates troubleshooting and future modifications to the electrical system. In conclusion, performing accurate short-circuit calculations is essential for ensuring the safety and reliability of electrical systems. The point-to-point method is a valuable tool for this purpose, but it is important to understand its limitations and to use it appropriately. When using multiple conductors per phase, it is crucial to adjust the F factor correctly by multiplying it by the square root of the number of conductors. Additionally, it is important to consider ampacity derivative factors, conductor temperature ratings, arc coordination, and arc flash hazards. By following these guidelines and consulting with qualified experts, you can ensure that electrical systems are properly protected from the dangers of short circuits. Remember that electrical work can be dangerous, and it is always important to prioritize safety. Always follow safe work practices and use appropriate personal protective equipment. If you are not qualified to perform electrical work, seek the assistance of a licensed electrician or other qualified professional. Safety should always be the top priority when working with electricity.